So today we're going to finish set theory. An exclamation mark is not a big enough punctuation for how happy I'm about this. Finish set theory. This is going to be somewhere in the range of section 6.2 / 6.3 / 7.1. Hopefully, we'll get 7.1. So anyway, though, let's talk about where we left off last class. In last class, we left off by we talked about a ton of logical operations. Everyone was there. Or not operations. We talked about a bunch of not logical or operations. We talked about set identities. Talked about we have like De Morgan's law. We have all of those still hold. Like basically everything from logic kind of carries over to set theory, which is really interesting and nice. But sorry, I was looking at the window. I realized by the time class ends, it's going to be dark. That's going to depress me. So I'm going to close the blinds. So I just don't even know what's happening. There we go. So we're talking about set identities. Let's actually prove one, right? Let's talk about how you would prove a set identity. It's really interesting and really not that hard. It kind of just goes over the same things that we have talked about before. But this proof, it'll show you how you prove anything really about sets. Like whenever you're trying to prove that two sets are equal or two things, or that, yeah, like really, when we're trying to prove two sets are equal, the thing we always want to go to is what we call the element method. And so the element method, we've been using it before, and I think in passing I mentioned it. Like I think I have mentioned it before, but let's just mention it again to be very clear. And that is, this is a proof technique to show set containment. Set containment means that one set is contained in another set, i.e. one set's a subset of another set. The way we can think about this is, i.e. this is how we show that A is a subset of B. And so let's remember that A being a subset of B, remember this is the same thing as for all X in A, X is in B. But that's like literally the definition of A is a subset of B. It means every element of A is an element of B. So the way element method of proof, the element method works, you say proof, and we prove the set containment basically by proving this statement. You prove this statement just like we prove any for all statement. But this kind of this is just like direct proof, section 4 point whatever. You just go here, okay, to prove that for all X in A, X is in B, let's go ahead and let X be any arbitrary element of A, and show that logically we must necessarily have that X is also an element of B. The property of X being in A will logically lead to the property of X being in B. So the idea here is let X be any arbitrary / particular element of A. And then we want to show that this logically leads to X being in B. And then we say, thus, by the element method, A is a subset of B. Basically, the element method, thus, the element method is kind of like just giving a name to this right here. Thus, since we have for all X in A, X is in B, that implies A is in B. Well, the point is, though, for all of our proofs, we're trying to prove that a set is a subset of another set. We can use the element method where it's just you assume you have an element in the smaller set and prove it to the bigger set. And then we say, by the element method, subset works. Any questions? Good. Okay, straightforward. I think that makes sense too. And so now, before we get into anything, let's also recall to prove A equals B as sets, we need to show that A is a subset of B and B is a subset of A. And the reason we want to show this is because if we know this is true, this means that for all X, X is in A implies X is in B. Yeah, so A and B kind of loosely means that X is in A implies X is in B. And B is a subset of A, well, that says that if X is in B, that implies X is in A. Well, heck, if you put that together, that's saying that X is in A if and only if X is in B, right? Well, and that's exactly what it means for the sets to be equal. It means they have the same elements. And so since X is in A, if and only if X is in B, that means A and B have the exact same elements. And so A and B are the same set. Any questions on all that? Good, that'll probably be the first video once I split this up in the YouTubes.